it means that travel at light speed is also impossible. Or is it? Mark Millis is one of a handful of scientists who isn't ready to throw in the towel on the subject. A NASA propulsion physicist by profession, he likes to build models of starships in his spare time, and is well aware of the giggle factor in any talk outside science fiction of star travel.
The giggle factor is actually a healthy response. It helps provide skepticism to the topic, to ask deep questions to make sure that we're proceeding correctly.
Once head of NASA's mothballed Breakthrough Propulsion Project, Millis is editor of a book that has collected the serious current research on the subject.
When it comes just to the light speed issue, there's about 36 physicists who've written articles, some skeptical, some suggesting new methods on the topic.
Albert Einstein's general relativity laws allow for the existence of wormholes. In 1930, Einstein and his colleague Nathan Rosen calculated the mathematics of one of these intergalactic pipelines. It became known as the Einstein-Rosen bridge.
The wormhole is a solution of Einstein's equations for general relativity, telling us how gravity works. They're hypothetical, and what they do is they connect different parts of space and time.
The Einstein-Rosen mathematical wormhole arose from studying black holes. A black hole is a region in space of extremely strong gravity. The gravity is so strong that there is no way for objects that get too near to break away from its gravitational pull. Nothing can escape a close encounter with a black hole, not even light.
This inverted fountain serves as a visual analogy to what's going on around a black hole. At the bottom is the area inside the event horizon. And the water falling into it is analogous to gas that might fall into a black hole. Imagine yourself being a fish swimming around this region. Once you get down inside this central portion, you're past the point of no return.
But Einstein never intended his wormhole as a tool for space travel. His wormhole is theoretically created at some moment of time. It opens up briefly, then pinches off. Anything that tries to pass through it will get crushed when it squeezes apart.
The typical wormhole that you write down in your equations and study is unstable. It'll vanish in an incredibly short time. So what you need is some means of holding it open.
Scientists began to investigate whether there might be a type of wormhole different from Einstein's that is traversable. But traversable wormholes needed something to prevent them from pinching off.
You want to stabilize the wormhole. You don't want the wormhole to collapse. Keep the wormhole open. That requires something new called negative matter or exotic matter. We've never seen negative matter before. It would have anti-gravitational properties. But one day, if we ever find negative matter, perhaps that's the key to stabilize the wormhole.